All right, I have this week's homework, and I went ahead and printed out your lab. Oh, I think that's just my original, sorry. All right, oops. Are there any questions before we get started? Any questions over last week's material? Feeling pretty good in here? All right, sweet. So let's start chapter 2. So if you've looked at the syllabus, you know that we're hopefully going to power through all of chapter 2 today, and then hopefully on Wednesday, chapter 3. And those notes are online on Blackboard. So let's look at chapter 2. And so we're starting off, so just what an element is. So an element is just any pure substance that cannot be broken down. And of course we have our periodic table here. And so we have, right, some synthetic elements over here, especially down. You notice the naming gets really weird. 113 and beyond. Let's see, yeah, they aren't even on that periodic table. And you might see different names later as they get updated. So these are all synthetic, so people just try to make new elements. So we have them all here. So it starts off with your lightest elements at the beginning, hydrogen, helium, but we'll take a deeper tour later. And so let's look at some elements that might be in the human body. And so you're mainly made up of oxygen, so you have a lot of water in your body as well, so you have a lot of oxygen there. Then of course we're carbon-based life forms, so 18% carbon, then going to be 10% hydrogen, then a little bit of nitrogen, and then so any others. So that could be, right, magnesium, need some iron, different minerals. And here's more breakdown. So, right, it's a lot of potassium. So potassium's good for like your synapses and making those connections so you can, you know, fire and move. So all those electrical impulses need some sort of ions to flow. So they need some movement. It's a little bit of sulfur in there. And of course, same thing with like potassium, you have sodium ions, so all just cations, chlorine, magnesium, etc. And so let's compare that to compounds. So does anybody know what's the definition of a compound? Yep, so 2 or more elements. And then we want to say, so they, yeah, define chemical formula. So we have to be careful with the word bonded. So I guess they would be bonded, but for example, like if you have sodium chloride, there's no physical bond between them, but they are just held by the electrostatic potential. And they are at least as a unit, so they would always be in a 1-to-1 ratio. But we'll get there as we continue, but this would be considered an ionic compound versus molecules where they are physically attached. So. But yeah, define chemical formula is a good definition. And I think y'all gave me lots of examples last time. I'll just put some more on there, right? Silicon dioxide, we mentioned NO, or you could do carbon monoxide, carbon dioxide. You could get into, chemistry is always ends up being drug talk. So it could be anything from caffeine or like cocaine, again, as long as it's a defined chemical formula. And so we also have different ways of representing our atoms and molecules here. And so this, for example, is just our like ball space filling model. And so the little white balls here represent hydrogen, and the red ball is oxygen. So you could redraw it like so. So you want to kind of be comfortable seeing it in different ways. And of course, this is just water. H2O, write your formula. So same thing with this compound. So we have our two black balls here represent carbon. So carbon is always black, and then hydrogens are always white. And so oxygen, let's go through a few colors. So oxygen is always red. And then other things in that family. So you have oxygen, and then you have sulfur, selenium, and sulfur is usually yellow or anything lower. So carbon, like we said, that's always black, so that's a good. Hydrogen is always white. And then halogens are represented by green balls. And what are halogens? So again, we'll go through this more as we take our tour, but we'll learn that halogens are going to be group 7. So we'll go back to them. So fluorine, chlorine, bromine, iodine, all of those can be represented by a green ball usually. And we'll stop here with our colors at least. So nitrogen is kind of the last one you'll see a lot, and that one is usually blue. So that will kind of help you. And so let's go back to this one, so we'll write our formula then. And so we have, right, our 2 black balls for carbon, so C2, and then 1, 2, 3, 4, 5, 6. So C2H6, so this is ethane. You don't need to know that it's ethane. This is an organic naming system. And we could also draw it in other ways. And so organic chemists like to be really shorthand and maybe almost cryptic. So this is also ethane. That's the exact same thing as this. And so it's just implied. So later we'll learn as we go through. So carbon, for instance, always has 4 bonds. And so anytime you look at this structure, you can kind of re-break it down. So we have just these 2 ends here, and I'll redraw it again explicitly. And so we had our 2 carbons there. And then so organic chemists don't draw in hydrogens unless they're on like other elements that are not carbon. But if it's on a carbon, organic chemists don't draw it in. But then you have to know to fill it in, since carbon always has to have 4 bonds. And so if it's just drawn like that, oh, well, we know that carbon has to be bonded to our hydrogens then. So that's just that structure translated in different forms. And so this is like a typical organic structure here. And so we want to be able to look at this and then write the chemical formula. And so we'll go through this one together and do some practices. And so just like we saw before, any endpoint here is going to be a carbon. So I'm just going to fill in, so CH3. And so with these structures, you want to be able to draw in like missing hydrogens so you can count it up and get your formula. And so if we look at this carbon, so it has one. So notice, right, any joint is also a carbon. So if it's bent, that's telling you there's a carbon there. Then we have 1, 2, 3 bonds. So then we know, oh, there has to be a hydrogen there that wasn't drawn. Then we can look at this carbon, 1, 2, 3, 4. It's okay, we don't need to put any hydrogens on there. This is another methyl group over here. This is a methyl group. And I'll just define methyl group. So CH3 is just a methyl group. That comes up a lot. And so again, I'm just going to write carbon, 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 carbon at every joint. So you remember that's a carbon, that's a carbon, that's a carbon, that's a carbon, carbon, carbon. And so now help me count up the formula. And so usually by convention, you start with carbon, hydrogen, and then proceed in like alphabetical order. And so nitrogen, oxygen. And so how many carbons do we count? So everybody count to themselves and then let me know. What do we get? You can show me fingers, how many carbons. So I see 8, 8. Do you have 8 over there? Excellent. So yeah, I get 8 as well. So C8 and then H. So now count up your hydrogens. Don't forget the ones we drew in. Actually, that's all we have. So I see 10. We all get 10. Excellent. That's what I got. And nitrogens, this should be easier. So how many nitrogens? 4. And then oxygens, 2. Excellent.
Where did you get the H's?
So
3, 6. You're counting the 3?
yeah, so that's where it gets tricky because each one of these has 3 on it. So 1, 2, 3,
Yeah.
and then 4, 5, 6, 7, 8, 9, 10.
Why are you adding the CH3 on? How did you know to add the CH3?
So when you have just like the little, so let's just examine, right, like the nitrogen has the methyl group there, it doesn't matter what it's attached to. So when you have just like a terminal endpoint there, first of all, that means that's a carbon. So then I draw that in. But then we said, well, carbon always has to have 4 bonds. And so in this case, right, it just has
So
1.
you're just adding 3 H's to the rest of the C.
Yeah, it's just how organic chemists do it. And so let's do another practice. So start with this square molecule. What would be the chemical formula of that? So, right, redraw it, draw it explicitly, add in your hydrogens. And I'll draw another one for you to practice. So let's go over the square at least. And so first I'm just going to redraw it again very explicitly now. And so now if we want to show every carbon, so carbon, 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 carbon. So we'll start with our little box framework. And then, okay, back to every carbon needs 4 bonds. So that means all of these carbons need 2 hydrogens. And so what was the formula that y'all got for this one? C4H8. Excellent. All right, so take maybe another minute or two to look at this one. So this one's kind of tricky. You got these weird double bonds going on, so make sure you draw it out carefully, count your carbons, count your hydrogens. I can just put on here. Thank you. Oh, yeah, all the weak stuff is there.
What are we currently on, by chance?
We're just starting chapter 2 today.
Okay, sweet.
And then ideally chapter 3 on Wednesday.
Awesome, thank you.
Okay, you can just throw it here. See, do we get, anyone have an answer for this? You know, just shout it out. What'd you get? C10H15N. I believe that is correct. So did everybody get that? So let's go over it. So the tricky part, also, does anyone know what this compound is by any chance? I picked it on purpose. So this is methamphetamine. We were talking about meth last week in lab.
I know what PCP looks like.
That's impressive.
And LSD. Those are fun ones.
Do you know how to make LSD?
No. I know what the compound looks like.
For
I
legal
probably
reasons.
could figure it out at that point, but.
No, LSD is actually really hard to make.
Really?
Yeah, if you look at the synthesis, because it has, what makes LSD complicated is it has 4 stereo centers. And so stereo centers are any carbon with like 4 different things to it, so it has chirality. But it's hard to control those stereo centers, so it has to be done under like different light conditions. So it's really sensitive. Meth, on the other hand, anybody can make meth. So. And so yeah, this is correct. So let's break this down. So we have this weird double bond thing. And we can also compare it to amphetamine. That's why I want to bring it up. Because they're the same thing. So while I redraw it, you can look at amphetamine. Oh, shit. Come on. Sorry, my charger is finicky. There it goes. Okay, back to charging. So this is amphetamine. And if you notice, the only difference is literally a methyl group there. So that's why it's silly to me that meth is so illegal.
And isn't amphetamine the base compound that they use in things like Ritalin and Adderall and stuff like that?
Yep. The only difference is the dosage. So methamphetamine is more potent because that little methyl group means that it can cross the blood-brain barrier a lot easier. So it's like, you know, it's like you could take meth as a drug, just like take less of it. But that's not how, you know, the drug classification system works, unfortunately.
We lost that number a long time ago.
Yeah, that's okay. I think they used to take like meth, like the Japanese kamikaze warriors. They would take meth so they would get, you know, amped up to go commit suicide. So, anyways, back to chemistry and analyzing compounds. So write out your double bonds. So that's kind of the first step to this. I'll draw this out. And so notice, right, each one of these carbons then needs a little hydrogen. This carbon doesn't, so it's connected to another carbon. And so I'll draw that explicitly, right? This joint right here is another carbon. Notice how it has two bonds, so it's missing two hydrogens. So I'll draw that in. Then we have our next carbon, so this one here attached to our methyl group. So again, that's our methyl group. Then that's attached to our nitrogen. And notice the hydrogen is drawn then if it's attached to like nitrogen, oxygen, sulfur, anything else, just not carbon. So they will draw it in then. So redraw that. And then again, the methyl group, the great methyl group that makes methamphetamine. And so like I was saying in lab, that's the simplest route to meth is you just start with the amphetamine and methylate it, and you're there. So super easy. And so when you redraw it out explicitly, you should get something like that. And so we'll just recount together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did I skip? Oh, 15 there. So see how I almost missed that one? So that carbon had 1, 2, 3. So it needed a hydrogen there.
Does the placement of like the hydrogen atoms like matter, like I guess kind of the order, or is like as long as it has to be next to like a carbon, it's okay?
So let me try to re-clarify your question. So do you mean like here? Like so you have this. Are you saying like does the angle matter
Yeah,
or?
does like the angle matter, or kind of the placement of it?
So I'll say kind of yes and no. So it does matter, but probably not for your case. Like I'm not going to be super picky, if that makes sense. I guess I'm not quite sure what question you're asking. Because you could redraw this as CH3, CH2, CH3, and then, right, you kind of just draw in the hydrogens like that, doesn't really matter. But there is, you know, 3D geometry.
Yeah.
And it's just normally like I don't say like, oh yeah, draw it out all pretty. Like I don't really care too much about that unless we were studying like a chiral center or really focusing on the geometry. But so let's look up propane. And right, so the idea is, so that's what it looks like on paper, but then, right, we can look towards these pictures to get a better like 3D sense of it. And so each carbon, and this is kind of going beyond today's lecture, this would be called sp3 hybridized, so they have what's called a tetrahedral geometry. So that kind of tells you where the hydrogens would be. And so just for like the simplest case, like methane, we could draw out what that would look like really nicely. So CH, CH. And then in drawing this, so this is showing 3D. So that hydrogen that I'm trying to make a fat wedge there is coming out of the plane of the board. And then if we do a dash, that's behind the plane of a board, again to show that 3D structure.
So wedge is in front and then dash is behind.
Yeah. But we'll probably revisit this later. It's just because you were asking. And so here's just another picture of, again, methane, so you can kind of see that 3D structure. But, you know, for our purposes, if you're just drawing stuff, you know, unless I'm really asking, show me the geometry, like, I'm not going to care if you draw it like that. Or just, you know, shorthanded. Does that hopefully answer your question, or?
I believe so, yeah.
All right. So I think that's compounds. Now let's look at back to our atomic structure and elements. And so now let's get into, well, what defines each individual atom? How do we know what they are? How do they arrange on the periodic table? And so we'll start off with what they're composed of. So all atoms are composed of the same subatomic particles. And so that just means they're made up of protons, neutrons, and electrons. And so protons and neutrons have nearly identical masses. So you're given the kilogram weights here, more for just fun facts. So you can see they're both about 1.67 times 10 to the negative 27 kilograms. And usually we just say they have a mass of 1 atomic mass unit. We'll see how that relates to the periodic table. And then for the electron, it's a lot smaller. So this is 9.1 times 10 to the negative 31 kilograms. And so when we talk about the mass of the electron compared to the mass of the neutrons, we usually just say it's 0. So we don't worry about the mass. So it's basically negligible for our purposes. And so the charge, though, of the electron is important. And so the charge of the proton and the charge of the electron are equal in magnitude but opposite in sign. And so by formal convention, the protons are a positive charge and electrons then are negatively charged. And of course, neutrons have no charge, so neutrons write neutral, kind of in their name. And so again, this is just a little chart breaking it down. So again, 1 AMU for proton, 1 for neutron, and essentially 0 for electron. And then we care about their charges. And then this would be their Coulombic charge if we wanted to find the charge of an individual electron. And so this is really important. So elements are defined by their number of protons. So just highlight that, say that. So if you change the number of protons, right, you change the element. And so that would be, right, like a nuclear reaction where you'd be changing the number of protons. And so again, the number of protons defines the element, and the number of protons is also its atomic number. So what does that mean? And so you might want to have your periodic table out. So in this case, you can refer to your little reference graphic here, but your atomic number should be somewhere in the upper left corner. And so notice that corresponds to its element number. So hydrogen has 1 proton in it, and it's element 1, so that's its atomic number. Right, helium then has 2 protons, so it's atomic number 2. So you can just keep going on and on and on. So like carbon has 6, so we know it has 6 protons. So again, that's super important. And so here's another just representation. So here's a helium atom looking at the nucleus then. And so you again have 2 protons in the nucleus, and they didn't label them, but these would actually be the neutrons then. So the neutrons are sitting in the nucleus. And so carbon, whew, oh my goodness. So carbon, so they're using blue to represent the protons. So 1, 2, 3, 4, 5, 6 protons. And you can tell 1, 2, 3, 4, 5, 6 neutrons, but we'll go back to neutrons.
So are electrons not in the nucleus?
Correct, they would be in the outer
Oh,
part,
okay,
yeah. So they're circling around the nucleus. So the nucleus is in the center, then the electrons are in the atomic orbitals, which we will go into. And so like you're studying on your periodic table, so you're noticing that elements are arranged in their periodic table by their atomic number. And so they're also arranged in this funny way so that elements with the same column have very similar physical and chemical properties. And again, we'll go into that. But this was also really important because it's how Mendeleev first started piecing together the periodic table. And so Mendeleev, right, he was an early scientist, and he was trying to isolate elements and kind of arrange the periodic table. And what was really cool about him doing this is he started noticing like patterns in reactivity, and so that's how he started arranging them in this pattern. And he actually predicted the existence of germanium before it was discovered. So you have like a little hole in his periodic table. It's like something needs to go there. So he predicted missing elements that were, of course, later isolated. So we have our atomic number. Again, it should be somewhere at the top or top left. Again, refer to your little key. And then we have our chemical symbol. And so that's just our abbreviation. So notice some of them are 1 letter. And then if they are 2, then the second one is lowercase. Yeah.
Slightly related, correct me if I'm wrong, wasn't he the first scientist to be alive when he had an element named after him?
Oh, I actually don't know that, but that may be true. I would have to look at fun random trivia. And of course, the name is there, and you should also have on your periodic table, so you have, sorry, I don't have my copy. Steal yours. So this one is very nice. I picked it for a reason, but I just wanted to go through it a little bit. So right, you have your atomic number, your symbol, your name, atomic mass. We'll look over this electron shell configuration later. It could help you in the future, though maybe not today. But what's also important, but I also don't want people to get overwhelmed or confused about, are in the upper right-hand corner, you have all those oxidation states. And so later we'll kind of go back and look at them, but I don't want them to be confusing, but yeah, they're there.
Can I get one of those periodic tables?
I will get you one later.
No worries.
So yeah, during recitation, I'll find it. And so let's look at isotopes. So isotopes, so first of all, right, we said, okay, number of protons defines the elements. However, all atoms of a given element, while they have the same number of protons, they may not have the same number of neutrons. And so first we'll look at this case with neon. And so there's different ways to write this. So you could write it like they've done so here. You could do like 20 neon just like that without writing the 10. So 21 neon, 22 neon. And so let's break this down. So this 10 here, right, that corresponds to the number of protons. And then the top number here, right, is our atomic mass of that element. And so you can see if neutrons contribute to the mass, right, so let's look at combination 1. If you have 10 neutrons, 10 protons, right, 10 plus 10 gives you 20, so there's your 20 AMU. Then 11, so now you have 21. And then, of course, 12 plus 10 gives you 22 neon. And so again, these are called isotopes. If you ever get really bored in lab, we have like a chart of all the nuclides and all the isotopes, so you could really knock yourself out looking at all those isotopes. And so again, this is one way to write the isotope very explicitly with the mass number on top, atomic number on bottom, and your chemical symbol. But like we mentioned, there's shorthand abbreviations. So this is another form. Let's do a little practice. So how many protons and neutrons are in the following? So we'll compare carbon 12 plus carbon 13 and carbon 14. So take just a minute or so, see if you can figure this out, and then we'll go over it. Let's look at it. So what do we get for carbon 12? So how many protons?
6.
So 6. And then how many neutrons?
6 as well.
And so we all got that right. So we could take we know the mass. And then if you're not sure what element carbon is, which I don't expect you to know, we just started looking at this, right? Go to your periodic table. 6, we know it has 6 protons. So 12 minus 6 is 6. Excellent. And how many protons are in carbon 13? So 6 as well. And then how many neutrons? 7. Excellent. And so just a fun fact, so the most abundant carbon is actually carbon-12. And let's see, looking at my notes, it's 98.84% abundance. And so all that means is, so let's say you could take out, right, 100 atoms of carbon and hold them in your hand or whatever. So about 99 of them, if you could then weigh them on a scale, would have a mass of 12 atomic mass units. And then, so carbon-13 only has about a 1% abundance then. So then, right, only one of those little carbons out of 100 is going to have a mass of 13. And so how many neutrons are in carbon-14? 8. And does anybody know what carbon-14 is good for? Dating. And so carbon-14, though, what makes it somewhat tricky. So this, first of all, has an abundance of about 1 part per trillion. So that's pretty small. But it's useful because it has a half-life of about 5,700 years. I think that means you can go back about 60,000 years in dating. And so the idea is, if you're an organic living organism, you're going to be incorporating, right, carbon into your body or whatever system. So you could look at this especially with like terpene synthesis. And so this would be the ratio that the carbon would be incorporated in your living body. And then once that living organism dies, then this carbon-14 is going to start decaying and decreasing. And so then they can just compare the ratio of carbon-12 and 14 and then try to estimate then a date. So that's kind of cool. Yeah.
I apologize if this was stated earlier, but what makes the carbon only have 6 protons?
So that's just kind of back to the identity, right? So it just means just if any element has 6 protons, then you know it has to be carbon. So that's like what makes the element. And then what's kind of weird, honestly.
It's on the table. Okay.
Yeah. And then the funny thing about isotopes too is like scientists are really unsure what causes isotopes. It just kind of seems to be a phenomenon. And if you kind of notice, like it's just kind of random which isotopes are more stable, which ones are radioactive. But if you kind of get like an imbalance, so right, you have 8 neutrons to 6 protons, then that might be unstable. But you notice as you get to like heavier and heavier elements, they'll have more of an imbalance in numbers, and it's kind of weird. But so that's maybe something to study. So we don't really know why they're isotopes, but we know they exist. And so see if you can answer this question. So what are the atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons? So I have to look at your periodic table.
The atomic mass is on the bottom, right?
Well, so actually this atomic mass we'll get into, but this is going to be an average mass.
Oh, okay.
And we can explain that in a second, what that really means. But so you might have to just do addition for that mass number.
Is the atomic number the number on the very bottom? Or am I getting it switched around? Like very,
So-
it's not on there.
So the atomic number is this number, right? So the total mass number for an isotope may not be there, but like I said, I'll explain what this number is and where the heck it came from.
Okay, hold on.
Yeah, once we do this. see, I think there's a marker up here. Does anyone want to come to the board and write down what they got for the symbol? Josh, you want to do that?
So the symbol, do you want everything or just the symbol?
Oh, like the whole symbol with all like the mass and everything on attached to it. Yeah, it looks great. Did everybody get this? And so, yeah, so did you see where all those numbers came from?
Yeah,
So we
now
pulled,
I see how they,
yeah,
so
so,
the final form, you put it that way.
right. And then, so the 17, notice, right, you pull that from the periodic table. And then our 35 is just our mass, so that's just protons plus neutrons. And so your hint there was the 18, so that was 18 plus 17 to get you to 35. And so that looks excellent.
That's your primary form of chlorine, right? That's the most common.
I believe so. I honestly mix up which ones are more abundant. At least on the chlorine. Oh,
I thought so.
yeah, because they're about in a 3-to-1 ratio. But let's actually talk about another isotope. Because you had a great question over what the heck does this number come from? And so let's look at a slightly easier element to look at, just because I honestly can't remember the ratio either. So I think it's about a 3-to-1 of 35 chlorine to 37 chlorine. But instead of telling you bad math, let's look at an easier example. So let's look at bromine. And so bromine only has 2 isotopes. So there's 78 bromine and 81 bromine. And so the significance of bromine and why I picked it over chlorine, even though y'all were knowledgeable of chlorine, is that bromine, these isotopes are basically in a 1-to-1 ratio. So 50-50, 79 bromine, and 81 bromine. So right, that means we take 100 atoms of bromine, we put them on the scale, 50 of them are going to have a mass of 79, and the other half are 81. So that makes sense so far? And so the next question is, well, what the heck is this number, and why is this number 79.9 and basically doesn't match with either isotope? And so what this is your average atomic mass. And so essentially what you do is you add up the percent isotopic abundance. And so you might have to do this at some point.
So if it's like a 53%, 79 with like a 47%, 81.
Yeah, I mean, your mental math skills are nice. So yeah, I would just estimate it to like 50-50 if you really want it to be precise. So you could set up the algebra, which I think that's what you were kind of doing in your head, it sounds like.
It was just an estimate. I'm not Rayman, I promise.
It sounded like a pretty good estimate over there. So you could set up, right, this is again just your percent abundance. So you could be given an isotopic abundance, so I'd have to tell you bromine 79 has a percent abundance of, I'll just say 50, but you could also do the algebra. And so let's say, right, you have 79.9 as your average atomic mass is equal to then 79, and let's just say times X percent, plus 81, and so if it's a percentage, that'd be 1 minus X. So that would be the algebra to get it super precise. Does that make sense to people? Okay. So So we could solve it, do it. And so going back to, let's just say carbon, so notice carbon, that's why carbon isn't exactly 12, it's 12.011, because 98% of them are 12, but then plus adding in that averaging for the 13 and 14 brings it up just a hair. And you can kind of use this to estimate which isotope is more abundant or not. So hence why the chlorine, you can at least say, oh, probably 35 is more abundant because it's mainly 35 in the mass. And we could do the math to do it more precisely. Let's just do the math for chlorine, since I couldn't remember the abundance. Let's calculate it. So 35.453. So let's go back to chlorine. So if we know the average mass is, again, 35, I already forgot, 0.43, 453 AMU, and we know that chlorine has isotopes 35 and 37. See if you can figure out the percent abundance of each. So see if you can do the setup and then start the algebra, and we'll go over it together.
So I'm confused. Does the X represent the average?
So X represents one of those percentages, right?
Yeah.
And so it only
Oh,
works
okay.
when we know 2. And so, right, the 2 percentages have to equal 100. So that's why I have the 1 minus X. So then you basically just kind of have to do the same setup for this.
I'm still confused on what the numbers outside of it should be. Outside of the X.
So then if we have isotopes 35 and 37, right, these are the masses of our 2 isotopes. So those should be those numbers that go on the outside.
Oh, so it would be 35 and then at 35 on the inside too?
So you would set up 35.43, and that's your average, is equal to, and we could do 35 times X. It doesn't matter what X is right now. And then plus 81 times 1 minus X, because again, it's a percentage, so we're just converting to that percent to a decimal. Oops, I put 81, I'm sorry. 37.
Does it matter which one has the 1 minus X next
Nope.
to it? Okay.
I'll just kind of write out the algebra at least. So do we get a percent abundance for chlorine 35?
You have time to answer by 100, right?
Yep.
Get a percentage.
So what do we get for chlorine 35 abundance? So you got 77% as well?
4, went the other way, 3.4 to 1.
So about 77.4%. And then 1 minus to get our other. So about 22.7 or so for chlorine 37.
You said 3 to 1.
I vaguely remembered. Any questions on this one? Don't be shy to ask questions, but
I'm just trying to, sorry, I spaced a bit. How'd you get, this, 37, chlorine to 37?
so then once you get your abundance of your chlorine 35, so did you get 77 for that one?
Yeah.
And then you just have to plug it back in. So you solve for x, and then you have to do just 1 minus x.
Okay.
So that's what I did right there.
Then you solve that then.
So if there was 3, would you just do 2 minus x? For your
No,
first
it
formula, or would
wouldn't
still
like
be-
work.
So you only can do that kind of formula for like a 2 isotope
Yeah,
style?
yeah.
Is there a different formula you can use for like more than that, or is it just get a little bit too?
You would have to use some sort of like systems of equation. I don't know if you can like remember back to algebra, because the problem with once you get 3 isotopes is then you have 2 variables. So then you would have to create some sort of system of equations where you could calculate that out instead. But I won't ask you to do that in this class. So for our purposes, I would just give you like a 2 abundance problem or something like that. Or, if we're going the other way, and we'll do practice in that, I think, in lab, but I could give you, the abundance of like 4 different abundances, let's say, and then you could calculate the mass. But I wouldn't ask you to do the opposite.
Okay.
Yeah. But you could, add them all up as long as I give them to you. Excellent. Also, I just want to praise you guys because your class is awesome, especially compared to my other class. Like, your math skills are good. Like, I'm honestly really proud of y'all. So let's switch gears in really quick to ions before I forget to talk about ions. And so ions are just defined as a charged atom, or we could say molecule or particle. I don't want to be exclusive, but right now we're just going to focus on our ions, our atom ions, I mean. And so just like we can have different number of neutrons, we can also have different number of electrons. And so usually they kind of make these defined patterns, which we'll look at. And so, for example, chlorine tends to make these -1 ions, meaning they have 1 extra electron loaded on there. And so we could also be, super explicit and have some situation like that. So we have an isotope, ion, so a bunch of information. And again, so this is just our charge. And let's analyze this chlorine 35 here. And so how many protons, neutrons, and electrons does it have? And so let's think about this for a second. So if it has a negative charge, that means that it's going to be gaining electrons. And so do we at least understand, so like for a neutral element, right, our protons and electrons are the same. So if I had just written out, let's just say 35 chlorine like earlier, so if it has 17 protons, then it has 17 electrons, right, because there's no charge, so positive and negative cancel each other out. And that means if we have some sort of positively charged compound, then you're losing electrons, because remember, you're not going to change the number of protons, so it's just in the electrons. And you can also kind of think of it like mathematically, that your charge is equal to, and so the way I think about it is protons plus electrons, but electrons, right, are negative, so you basically, add the negative of that. So that's how I think about it. So let's take a minute or so for this. So how many protons, neutrons, electrons?
And the one on top left is the atomic mass, right?
Yep. So what do we get for protons? 17. How many neutrons? 18. How many electrons? 18. So excellent. So you had one negative charge. We had to add extra electron to that. So let's try 2 more practices. So we'll do I may not have given you all the information, so you gotta go look for it. And I'm just going to run to the bathroom real quick. Too much coffee. Do we have answers? Yep, what'd you get for calcium?
For calcium, I got 20 protons, 22 neutrons, and 18 electrons.
Excellent. Everybody get that? Questions? No questions? And then,
Can you
oh,
tell me how he did that?
so calcium, I was a little mean. I didn't say the atomic number. So you at least have to glance at your periodic table. So you got calcium was 20. So you know there's 20 protons. Then 42 minus 20 gives you 22 for neutrons. Then we had a plus here. And so if we have 20 protons versus 20 electrons, let's just say for the neutral, but then you lost 2, then you get 18. You can double check yourself, 20 plus a negative 18 gives you positive 2. What about for sulfur? Want to go for it?
I got 16 protons, 14 neutrons, and 18 electrons.
I double checked what'd you get for electrons? Sorry. I spaced out and didn't hear.
20 neutrons, actually.
20 neutrons, I like that. Is that what we got? And then how many electrons? Sorry.
18.
18. I like 18. Yeah, 18. All right, do we feel comfortable with that? Questions? All right, so now we're kind of going to start our, what I like to call our tour of the periodic table. Let's see. So I was saying how I want to do my tour. So let's look at our periodic table of the elements over here. Oops, oh my gosh. And so down at the bottom, we have some sort of key. So I like this version for this purposes because this goes into more detail. So we have our alkali metal over here at the front. So group 1. And I'm pretty sure everybody knows what these are famous for, but what are they famous for? Try.
I know they're super reactive.
Yeah, that's what we're looking for. So they're reactive to water. So that's what they're famous for. So as you go down the periodic table, they get more and more reactive. So lithium just like will fizz in water. Sodium starts getting more of a fireball, at least with enough mass, and kind of runs around and shoots off orange sparks. Potassium will really ignite with water, so it's pretty explosive and gives off like purple flames. And so potassium too is your last limit of where you can cut in air. And yes, potassium will auto-ignite potentially if you slice it open and expose it to air. It is very angry, nasty, will react. And then once you get to rubidium and cesium, then they become so reactive that you actually can't handle them in air. And I'm sure if you get bored enough, you can look onto YouTube and find videos of it exploding. Oh, come on. And so here's an example of how rubidium would be stored. So notice it's in an ampule here. So this is a glass ampule. And so in a lot of videos, they'll take that ampule and just like break it directly into water and like it explodes. And so if you actually wanted to work with rubidium though, then what you would do is, so it's in this nice little ampule, and you take it into what's called a glove box. Let me just put a glove box. And so something like this, oh, that's an old one. This is a nicer one. And so, no, go away. So basically you have these these are little antechambers. This is a small one. This is a large one that takes a lot longer to pump in and out. But you would probably take that little ampule through here. And so all this does is has a evacuating to a vacuum pump. So you suck it down, and then you refill it with nitrogen 3 times, make sure it's nice and clean. And then this glove box here is usually a nitrogen atmosphere. If you were Gucci and doing a really strange research, you might do argon, or you're just a rich lab, you have money to waste, then you could do argon. And so they usually pick nitrogen because nitrogen is fairly inert. The one compound, though, or one of the few compounds that it can react with, though, is actually lithium, funny enough. And you make this lithium nitride, which is blue. It's kind of fun. Let's look at lithium nitride. These have a picture of it. Oh, come on. That's annoying. But basically lithium, your little lithium metal will take on this weird like blue sheen, which is just lithium nitride. But yeah, so that's basically water reactive, and of course, as we go down the periodic table, it gets more and more reactive. And so next on our tour is the alkaline earth metals. So those are all these. And so they also tend to be kind of water reactive, but not as such. And so some people usually say like acid reactive to show that they are less reactive than their alkaline metals. But like magnesium, calcium, so those will react readily with acids, strontium, so same thing, they'll all react and dissolve.
So is that alkaline earth? Is that what the word is?
Yeah, alkaline earth metals. And so this block in the middle, so we won't spend too much time on this in this class, unfortunately. So these are all our transition metals. I like to say this is where the fun happens, but again, I'm biased. I'm an organometallic chemist by training, so this is what I like to work with. Iron, cobalt, nickel, all these are fun or irritating depending on your opinion of the day. And so we won't talk again too much about it, just there's a lot of fun colors involved in these elements. They can be used in like firework displays too. It's lots of fun stuff. They do catalysts. We'll skip over them. And so now we have, so notice too, as we go from left to right here, we start with really metallic character, and then they slowly become less metallic. And so over here on aluminum, gallium, indium, so this is still metal, and you can kind of carve that out. And then you have, right, our stair step here, boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. So you can kind of isolate those out. And so all those are your semi-metals. And so these tend to be, right, have properties of both metals and non-metals. A lot of them are also used as like semiconductors. So, right, silicon is used a lot in chips, same with germanium. And so once you cross this, so now you're into non-metals. So note the blue change in color. And I'm kind of difficult. Hopefully no one's colorblind or has difficulty. You know, I once had a professor of geology that was colorblind. I was always fascinated like how he did it. There's so many gradient maps that are colored in geology. Anyways, so right, all these now are non-metals, and let's pull up our P table. Except now I've lost it, too many windows.
So those are called semi-metal metals?
Yeah, so these are all your semi-metals, kind of your stair step. Again, your metals versus non-metals, so they're in between, they're bridging the gap. I don't like how this website doesn't do what it used to do. It used to just be if I hovered, it would give you a cute little picture. I don't know why it doesn't do that anymore. Because that was convenient, so you could look at like carbon is obviously like a black powder. Oh, let's actually, so I should have mentioned something earlier. So carbon, let's talk about carbon for a second and allotropes. And so allotropes, all this are different geometrical arrangements of an element. And so thinking back to our classification of compounds, so carbon, it has different forms, but I want to be clear, all those would still be considered elements. So for example, you have carbon C60, and so even though, right, there's 60 atoms in this one element, right, we don't consider it a compound. So it's just one atom, so it's still just an element, so it's still an element, so I just want to emphasize this. But allotropes are just, again, different rearrangements. So if I could find, so let's go back to carbon. Oh, come on. So going back to Wikipedia, looking for pretty pictures. Let's see. There we go, okay. I'll look at your separate page. So pretty pictures. So D here is the one that I had written for you. So this is a Buckminster fullerene. So this was the first buckyball. I think something is labeled. Oh no, this is the buckyball. Sorry, I can't read. So D here is our buckyball. So it kind of looks like a soccer ball. And so this was a new material that was invented at Rice University, and that kind of launched all the nanotube research that is going on there. So diamond, for instance, is an allotrope of carbon. And so what's kind of fascinating about diamonds, I don't know if you can tell from this little depiction here, but all it is tetrahedral arrangements of carbon. So just repeating. So I'll add diamond. So again, still just an element, but we mentioned, right, carbon has that tetrahedral structure. And so in this diamond form, it's just repeating tetrahedral units, and that gives diamond its strength. And so you're probably most familiar with graphite form of carbon. And so notice graphite, notice how they're in sheets. And so that means that since there's no bond between them, it's just intermolecular forces. So when you put your pencil down, you can easily shear off. And so that's how you write. So you see the structure of that. I don't care about that one, blah, blah, blah. And so you may want to look at like the carbon nanotube. So this would be, again, another allotrope. And so this is based off of this buckyball, where then they were able to start growing carbon nanotubes. And let's look at so another one with famous allotropes is phosphorus. So again, still just phosphorus. So it's just made up of phosphorus elements. But you have, right, white phosphorus. So that was used in military, so that's more explosive.
I was gonna say, like, wasn't like phosphorus used by military or something?
Yeah, so this allotrope, yeah, so that's white phosphorus, so people
We're on the same page, it's against the Geneva Convention.
Because everyone follows that, right?
We do.
We
For
do?
the most
Okay.
part.
That's good to know. So yeah, this one, pyrophoric, flammable, so that's, ignites in air. So clearly y'all know about that.
That's nasty stuff. They used to show us videos of how bad it is, because other countries still use it.
Oh,
They
man.
show us 'cause we have training on how to avoid it.
Oh.
That stuff is nasty. You'll see people with the chemical burns on their skin and stuff like that, going blind and stuff like that. That white phosphorus is nasty.
Yeah, it is. And so meanwhile, then if we compare that to red phosphorus, so red phosphorus now in its arrangement is more stable, and so it's fairly thermodynamically stable, but apparently less so than black phosphorus. Let's see.
Who thought heating up white phosphorus was a good idea? 'Cause
I mean,
here's this toxic chemical. Let's heat it up.
there's research devoted to bombs and explosives, so yeah.
Okay, true. So hopefully they're being safe, not like some dude in a tank top flip flops. Let's see if I heat this up.
Well, I mean, maybe, back in the day, chemists were like way more loose. Like, they would be like literally smoking cigs in the fume hood, like doing the benzene dip. Like, chemists were crazy back in the day.
You also have to realize the time that white phosphorus became a weapon was in World War II, and you also have to realize those are the same people who were using ammonium chloride and mustard gas and a whole bunch of different stuff regularly. So,
They probably lost a few brain cells.
if they were lucky.
Yeah. And so just to continue our discussion, there's black phosphorus too. So again, different structure. Still phosphorus, right? Still an element. So the point is just you can have different geometrical arrangements of these elements with obviously very different properties, from explosive to just not.
I find it interesting though. So black phosphorus and red phosphorus less deadly than white phosphorus?
Yeah, so I don't think they explode. See, so this one is stable, blah, 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 at least relative. Yeah.
So ideally, if you heat up white phosphorus enough, it becomes less deadly.
Yeah.
But it's heat and pressure, if I remember correctly. You have to keep it pressurized, right?
I think you probably would have to. Let's see. Well, it says you can make red phosphorus from white phosphorus. You just have to heat it, but you just can't expose it to air. So I think once a white phosphorus gets exposed to air, that's where you get the explosive. So if you just heat it in a glove box environment, then you can make the different forms.
Glove box in a car.
What glove?
I just got someone putting white phosphorus in a car glove box and just shut it in and heat up the car.
Not that glove box.
It could work if it was sealed correctly.
You guys are funny.
That'd be a horrible Uber ride.
Yeah.
That chemical burns 0 out of 5 stars. Geneva.
All right, let's look at, so back to our tour. So we were saying now they're getting more like non-metals. So of course, nitrogen's a gas. We went over phosphorus. And so this is group 6 here, which I like to affectionately call the smelly family, smelly elements. And so obviously oxygen doesn't smell, but we breathe it, so that's wonderful. And then if we go down, so sulfur does get smelly. It's actually not pure sulfur itself, but hydrogen sulfide starts smelling. And then, so any compounds of selenium and tellurium are going to be super nasty, garlicky smelling compounds. If you were to accidentally ingest one, which you would not want to do, you might have some weird garlic odor breath. and I believe it was tellurium. There was a chemical plant, and they were making it, and like a small bit of tellurium compound got released, and it caused like a big evacuation of the town. Like it was just super horrible and smelly. So all these are smellies. Good way to identify them. And so group 7, we mentioned, so those were the halogens represented by the green ball. And so all these halogens are fairly reactive. Let's go back to our periodic table.
What's like those like train stink bombs? Will those be made out of those elements or?
Probably not, because these would probably be like way too smelly. Maybe they would be sulfur based, but I would have to look up what's in.
I wouldn't think like a stink bomb be made of like pure sulfur.
Yeah, I mean,
That'd be a bad idea,
it'd be pretty smelly.
especially in a chemistry lab.
Let's see, so we look at fluorine. So fluorine is a gas, and so here for this picture, they've condensed it at a low temperature. So this is liquid fluorine. And so fluorine's pretty nasty. You need like again, it's a gas normally, so you have to have special regulators. You know what a regulator is, like a gas regulator? Okay. And so those have to be like corrosion proof for fluorine, so pretty nasty. Chlorine is also fairly nasty just to use. So again, chlorine would be a gas. And so you could also, again, use it as a gas form, but you need a regulator. You could also try to make it, but pretty nasty. Chemists tend to prefer bromine. So bromine is used a lot in synthesis. And so what makes bromine a lot nicer is, so bromine is a liquid. It is still a fuming, angry liquid, but you can still pipette it over and add it to your reaction. Yeah, it's like a nice brown gas.
Yeah, I use that. That explains a lot.
Yeah, so you definitely want to use a fume hood if you're ever working with bromine or any of these. And so iodine is kind of cool. So I think iodine might be one of my favorite elements I've come to realize, just because it's so pretty. So it's nice and shiny and solid, and it's kind of this weird metallic gray violet thing. But what's also cool about iodine, and hopefully we'll see that in lab on Wednesday, is so iodine tends to sublime. So if you have like a little bottle of iodine, you'll get crystals up top. So sublimation, right, goes from solid to gas, and then it'll recrystallize on the top. So you get like nice purple iodine crystals on the top of your like caps or something. And so unfortunately though, due to Breaking Bad, iodine has now become a regulated substance because it's a way to make meth. Surprising, you can make meth by so many routes. So yeah, now it's a regulated substance. Obviously this is used a lot in like the hospital setting too for disinfectant in a solution form, but the crystals are more regulated.
I believe this one, like algae medicine, was like banned and not regulated for the same thing. So it could be used to make meth with. Which begs the question: can you make like meth with anything at this point? Like
A good organic chemist can make meth from a lot of things. So a bad one can only make it from amphetamine. They only know how to methyl. Yeah, like methylamine became super regulated after Breaking Bad. Does everybody remember methylamine? Did people watch Breaking Bad? Yeah, but methylamine was that compound that they stole from the train. Yeah. It's a nice compound. Honestly, I wanted to use it as part of my research. Right, because that's just methylamine. And so amines are used a lot, and I was like, man, it'd be nice to just have a small functional group. No, can't do it. Anyways. That's how I feel, is dang meth labs. Making everything a regulated substance, making...
stealing art.
Yeah.
There's so much stuff, and every time they regulate one,
thing, they just find something else to replace it.
Yeah, it's like solvents get regulated. It's too much for me. All right, let's take what I'm going to call our second tour of the periodic table, and we'll see how far we get today. And so now we want to look at the electronic structure more closely. And let's start off, so let's look at, we'll start with hydrogen. We'll start simply. And so I'm just highlighting all of this. And so this is what's called our S block. Well, first of all, what the heck are you talking about? And so we said that electrons exist in these atomic orbitals. And so now we have a really sophisticated picture of our orbitals. So first we had, just very simple. We have a nucleus in the center and the electrons kind of float around. But now with quantum mechanics and computational chemistry, we have a much better picture of what's going on. And we have what's called, so this is just our quantum number L here, L equals 0. And all this means is that we're referring to, we have an S orbital. And so every energy level has an S orbital. And so let's just start right, this would be like our first energy level. So I'll just label this 1s. So everything starts off with an S. And so this is also going to be the lowest energy orbital. And so we're just looking, again, it's a spherical shape, anything that's S. And so in this case, so I'm going to flip over. So as we do this, we want to practice our electron configuration. But if you go to this P-table website, you'll notice that this will help you greatly. And so what I mean by that, so if you click over to electrons, now it kind of changes modes. And so I'm looking at hydrogen. And so notice over here, it has the same information that we're about to go through. And so again, starting with hydrogen, all we have is an S orbital. And so those electrons are going to go into the S orbital first. And so we can write then our electron configuration for hydrogen as just 1s1. And so this 1s is telling us, right, which orbital is being filled, and then this 1 indicates how many electrons. And of course, we're looking at hydrogen, and it's just neutral hydrogen, so 1 proton, 1 electron. So now what's kind of confusing is maybe the placement of helium, but we'll kind of discuss this placement. So it really, oops, I'm on the wrong tab. So helium, in some ways, should be hanging out over here with the S block, but it's also here with our, right, noble gases. And so why it's there is because it tends to be unreactive. And so why they're unreactive is because they have their shells completely filled. And later we'll call this the octet rule, which you may have heard of. But helium is a little different. And so it's satisfied by what we call the duet rule. And so all this is saying, so we have our S orbital. So that's supposed to be my 1s for helium. So both of my electrons are going to be somewhere in that sphere. And then we'll write our electron configuration, so 1s2. And so the other thing that we need to know is so we can represent a 1s orbital like so. So just one little line here. And that means that the s orbital can only hold 2 electrons total. And so we can kind of rewrite this representation. So you want to get comfortable with different ways of seeing this. So you could see it like that, same information. This is just showing 2 electrons. Notice too that I put the electrons with opposite spins. So that's just something from quantum mechanics. So you can't have 2 electrons occupying the same position. So meaning like that, that would be a violation of quantum mechanics. So that doesn't make any sense. And so that's why I draw them with opposite spins. And by convention, electrons are just half arrows. And so it doesn't matter if they're up or down, you just can't put two of the same spin. So for example, right for hydrogen, then I could draw it 1s. I meant to draw it upside down. Like that, doesn't matter, right? It could be in either spin up, spin down position formally. Doesn't matter. All right, so are we following so far? Because this stuff can get kind of weird, but I teach it all together, and so hopefully if it clicks, but ask questions early. All right, so now let's go to our next row. And so now we're going to what would be, right, our next energy level. And so, right, okay, we have to start back over at the s orbital. So now this starts our 2s. And so all this means, and let's actually go to our P table here. So now we go down to lithium. And this is what I was looking for, this little spear down here. So you can tell, right, we have our first 1s orbital. It's still in the core. So now it's going to be called, right, our core electrons. And so again, looking at lithium, so it's atomic number 3. So now we have 3 electrons. So those first 2 go into the 1s, and then now we have our 2s. So now it's like another onion ring ball around it. There's a little bit of space between them. And then it starts our next 2s there. Yeah.
I'm looking at the textbook and it says something called period. Is that the same thing?
So that just refers to like the rows. So it's like kind of the same thing, but we're looking into like more detail then for those periods.
Okay, that makes sense.
Yeah, and you'll kind of see what I mean by that as we go through it. So then we start the 2s. So let's write our configuration for lithium. So now it's 1s2, 2s1. And so you can always double check yourself. So your little superscripts should equal to your total number of electrons. So lithium has 3, so 2 plus 1 is 3. And then we can also practice writing it in our other method, kind of our energy level diagram method. So you always fill the lowest one first, so 1, 2, and then 3 there. And sometimes you see it in like weird block forms too. I think your textbook does this, like 2s, 1s, something like that. So just be aware of all the different ways they can kind of say the same thing. All right, so lithium, beryllium, so right, this is 2s2. And so now we're going to leave the s block. And so let's move on over to this p block here. So now this is your p block. And so let's see what that means. So you have 3 types of p orbitals. And notice they just go in your directions x, y, and z. And so x usually is going across, y comes in and out of the plane of the board, and z goes up and down. And usually it's also the principal rotation axis. Yeah.
Just real quick, is helium part of the S block?
Yeah.
Okay.
So that's what's weird about helium. Even though it's like over there with the p block side, it doesn't have any p orbitals. So principal rotation axis. I just threw that in there. You may see that term in other cases. And so now let's go back. Oops. Lost here. And so again, our 3 p orbitals. Well, each p orbital, so each p orbital can hold 2 electrons, and then there's 3 of them. So that means the p orbitals can hold 6 total electrons. And you can always remember that, though. So if we go back to our periodic table, how many across is this p block? 6. And so exactly that corresponds then to our 3 p orbitals. And so let's look at how you would fill this up. What is going on?
Siren or something?
You see anything?
That probably right to the 4 o'clock. Looks like a police car in disguise.
Is that why it has a weird siren? Oh, yeah.
Yeah.
Okay, now we all have ADD and we're distracted. So anyways, so back to boron. So now we're looking at boron. And so it has 5 here. So again, we start always at the beginning because you always have to fill up from the core. So you start with the 1s. So 1s2, 2s2, and then now, again, note that your p starts at 2. So you don't start at 1p, because what you're saying and what this means, so our first energy level does not have any p orbitals. So your first energy level just has the s. And then now that we go to our next row, now we can have p orbitals. So we only have in our second energy level s orbitals and p orbitals. And so we'll go 2p1. And so then how we want to draw this out in our other form. So 1s, 2s, 2p. And so you draw, right, 1 line for each. Then your p, again, there's 3 of them. So you draw out for your 3p orbitals. We can write this information like so. So 1, 2, 3, 4, 5. And I just formally put it in that one. It doesn't really matter what orbital it's in.
Is that a 7 or a 1?
This, it's an electron.
Electron.
So a half arrow. So
okay.
neither a 7 nor a 1.
Lost the clock. Okay.
Yeah, and so like you had mentioned, right, with each period, so each one of these corresponds to a period. So a period, that's super distracting, is just a row, right, in chemistry. So it's just a fancy name for a row. So that's all we're doing. So now, right, second period.
Hey,
Oh.
the S, I mean, okay, so the 1s orbital is which incorporates the 2s?
So the 2s starts at lithium and beryllium. So they're the only ones that have
Just
at least end in the 2s. So everything after beryllium would still have the 2s, right? Because you always fill up your lowest energy levels first. But it starts
the 2s
there.
is only those 2 elements?
Well, this is where it ends. But I just want to make sure you understand. So let's go over to this periodic table. So like let's look at boron, right? We were on boron, but we have to fill up, right? Oops. You have to fill up the 1s, then the 2s, then you go to the 2p. Does that make sense? And so, right, if you continue down, so notice how they're filling. So let's look at nitrogen. So we have them, they're in different p orbitals, and you probably have heard this in your like chemistry classes of the candy rule or something that everybody needs. a piece of candy. Does that sound somewhat familiar to people?
What is that other symbol besides the half arrow?
Which symbol?
The symbol, after the half arrow, like the little curve, like it looks like an L?
This one?
Yeah,
It's another half arrow.
another half arrow. Okay, so it's going down, okay.
Yeah.
Not bad.
So then for nitrogen, so we're almost out of time. So we're at 1s2, 2s2, 2p3. But then when we go to fill that up and we write out these orbitals, so let's write them out, 2p, 2s, 1s. So again, you always start from the bottom. So 1, 2, 3, 4. So we filled up that. And then, again, you probably heard someplace, oh, everybody gets an electron before they pair up. And that is correct. So now we're going to really analyze why that is so. So these energy levels are called degenerate, which just means that they're the same. Huh?
Is it just roasting them?
So yeah, so these are called degenerate energy levels. But the issue and why you have that candy rule that everybody gets an electron first is because in order to pair them and put 2 electrons in one orbital, you have to pay an energy price. And so that's not favorable. So the first thing that it's going to do is fill up, right, those individual orbitals first. And then, so once we cross over to oxygen, now we are over time, I apologize. I'll finish this thought up. And so now we get to oxygen, and then the pairing begins. So then we can fill it up 1s, so 1, 2, 3, 4, 5, 6, 7, then 8 there, so 2p4. And so one of them is paired, doesn't matter who, we're just showing there. All right, so we will have to end here due to time, so we'll pick up on Wednesday with the rest of chapter 2 and hopefully dive into chapter 3.
Do the numbers mean like how many half arrows there are in there?
Yeah, exactly.
Oh,
So these
okay.
are, and remember the half arrows are just electrons. So
Yeah.
this is just how many electrons in each orbital.
Now it's clicking in.
Yeah, that's right. It's good to go slow and ask questions on this part, because if you like miss the fundamentals of this, then like the rest of chemistry will be confusing. But if you have a good solid foundation of all these electrons and how they fill up, then you'll start recognizing patterns too, and everything will click.
I'm starting to get like flashbacks from high school from this. Okay.
Hopefully good flashbacks, so not PTSD or anything.
Teachers, but,
All right, I will end here, so I'll stop the stream. And of course, if you have questions,